The following content is supported by victoris.org.
Hi everyone, my name is Chen Hao and today I'll be talking about tangent spaces of manifolds. So I'm going to assume you know the definition of a manifold. A manifold M is a collection of points P with a topology on it, and briefly speaking what that means is that there's a set of coordinate charts that cover the entire manifold such that every point P will be contained in at least one coordinate chart. These coordinate charts are homeomorphic to RD, so for every one of them there's a homeomorphic map, which means that it maps open sets to open sets, and it's homeomorphic to RD, where D is the dimension of the manifold. So the fact that every point P must be contained in at least one of them means that the collection of charts, which is also known as the atlas, must cover the entire manifold. There must be no point left behind. This coordinate chart definition over here also gives a rigorous definition to what we mean by the manifold is locally Euclidean. Now for every intersection between two coordinate charts there's a compatibility condition, and this compatibility condition imbues the manifold with a differentiable structure. With this differentiable structure we'll be able to construct the tangent spaces of a manifold at every point P in the manifold. So let's first talk about motivation. When you get out of bed, why do you want to define the tangent space of a manifold? We want to define manifold tangent spaces because if we have a point P, perhaps it could represent a particle living on a manifold M. In order to describe the dynamics of the particle, we need a rigorous definition of vectors. We need to say that the particle is moving in some direction V along its world line, and we want to be able to say that this vector V will mean that in its next time instant, right, it's going to move to some other point on the manifold P prime. In other words, the tangent vector is a way to map from a point P on the manifold to another point P prime on the manifold, essentially near P. In addition to that, right, a vector is an element that lives in a vector space. And what's something we know about vector spaces is that any two vectors A and B in the vector space V can be added together to give another vector in the vector space. On top of that, we also know that any one of them can be scaled to give another vector in the vector space. So we would like to make precise the notion of adding two velocities V and W to give some composite velocity V plus W. And this velocity V plus W must also be able to transport a point P to a nearby point P prime in a rigorous way. It will turn out that curves is the necessary structure that lets us define tangent vectors. How so? If we have a curve gamma on manifold M, it's defined as a map from some interval, it could be the real numbers, to M, such that it maps every parameter lambda to a point gamma of lambda on the manifold. Now there's infinitely many curves that you can define on a manifold, and that means that there's many curves that pass through a given point P as well, many such curves. These curves have a direction given by the increasing value of lambda. And what's useful from this definition? We see that if there is point lambda of P that maps to P, then we can essentially add a small value to lambda of P, let's call it epsilon, and that will give us a point that is very close to P prime, that's a point on the manifold as well. So our curves over here allows us to move a point P to a nearby point P prime in a rigorous manner. It will turn out eventually that we actually want to say that curves have a one-to-one correspondence with tangent vectors, but at the moment there's quite a lot of issues that we have to solve first. Notably, there can be many curves that pass through a point P that bring you to the same point P prime. So an example is like this. We can see that these two curves, they pass through point P and they also bring you to point P prime when you move a little bit away from lambda P. But after that, they go their separate ways and they might even intersect in future. And then there'll be a problem when we want to find the tangent vector at this point. Which definition do we take? In other words, we see that this problem of many curves being able to map to the same tangent vector would mean that this one-to-one correspondence isn't well defined. It's more like many to one correspondence. This will eventually be solved when we define equivalence classes of curves, but we'll cover that later because it requires a definition that we'll build up towards. Okay, great. Now we've defined roughly what a tangent vector is, but there's still no rigorous way to add up two vectors together. How can we say that we want to add up curve gamma 1 with gamma 2 when there's no addition algebraic structure defined on M, right? How can we add 2 points on the manifold M? This actually motivates us to actually define the tangent vector as a derivative instead. So what I mean is that instead of working with curves directly on the manifold, we actually want to say the derivative is a tangent vector. Now this is starting to get really weird, right? So let's try to tie down things to a concrete concrete realization by introducing functions on manifolds. So when talking about functions, right, we'll bring rigor to this notion of a derivative as a tangent vector. So functions on manifolds are simply mapped from M to R. An example would be the temperature or pressure or like the electric potential. I'm going to use scalar function and temperature interchangeably because I want to abbreviate hotter with and colder with how the function changes along the curve. So when I mention temperature and when I mention hotter or colder, I just mean function, right, on the manifold interchangeably. This does not affect rigor in any way. I'm just using temperature so I can use English to describe it more intuitively. So functions on manifolds are just like this, right? How do functions change along the curve? Namely, because our curve gamma brings us from an interval to the manifold, and because our function f brings us from the manifold to the real numbers, right? If we compose these two functions together, we can see that f composed gamma is actually a function from the interval to the real numbers. Now we should be screaming with joy because on the left hand side is a real number, on the right hand side is a real number. This allows us to take derivatives, so we can rigorously say the derivative of this composite function with respect to the parameter lambda. This is well defined. So this actually lets us start with a definition, right? We want to define that given a curve gamma, we want to define a vector v of gamma. And at this moment, right, it can be a many-to-one map. We'll talk about that later in equivalence classes. But for now, right, if we have this machinery that eats in curves and spits out vectors, how do we define these vectors, right? We see that they act on functions f. So this v of f, right, is defined by how it acts on a function f. And how it acts on a function f is as follows. And we evaluate this at lambda equals to lambda p, where lambda p is the point that gives you gamma of lambda p mapped to point p. Now this definition may seem a bit mind-boggling, but actually the important part is in just this derivative over here. For all purposes, you can think of this tangent vector as this derivative. Okay, that's great and all. Now we have curves and we see that there's a mapping from curves to tangent vectors, but we still want a way to add our tangent vectors together. If we have a tangent vector d over d lambda and I add it to another tangent vector d over d lambda prime, right, I want a way to say that this gives me some vector of sorts. When we learn in linear algebra, right, when we have a vector, they can be represented abstractly as arrows, and we can add two arrows together by putting the tail of one with the head of another, and that will give us this composite vector that's the sum of these two vectors. But when we do actual calculations, right, we usually expand the vector in terms of a basis. We say that this vector has the components of 1, 2, 3, and this vector has components of 3, 2, 1, and we add two of them, add it component wise, which will give us a vector of 4, 4, 4. So what we are seeking, right, is we are seeking a basis such that we can break this into some components v1 along with some basis e1 plus v2 e2 plus v3 e3, and of course this continues to as many dimensions as we have in a manifold vd ed. Now I'm going to spoil it for you a little bit and tell you that the basis vectors we're actually seeking, e of mu, is actually the partial derivatives with respect to the coordinate chart. And this expansion is actually the chain rule, d over d lambda equals to dx1 over d lambda, partial derivative x1 plus so on all the way to, or written in summation notation, and we often actually drop this summation and adopt the Einstein summation convention, but I'll not talk about that in this video. But let's step back a little bit, right? Let's hold on, right? And let's see how this is even defined rigorously. Now whenever you want to do something rigorously, you step back into the coordinate charts that we had previously. So let's consider what definitions we have to work with. So remember that we had a manifold M, and there's many coordinate charts, right, forming an atlas, and one of them, right, let's just say it is phi, is homeomorphic to RD, and homeomorphic means that there's an inverse as well, and living in this RD, right, is our coordinates 1, x2, all the way to xd, which I'll conveniently denote x mu. In essence, right, our phi's are a map from M to RD, or to be more precise, actually a local subset U, where U is a subset of M to RD, and our phi inverse is a map from RD back to U. Right, then besides that, once again we had our function f, which goes from M to R, and we also had our curve gamma, which goes from the interval to M. Now when we write something like that, we need to understand what each component means rigorously. So actually the derivative on the left hand side, right, is of our function f, right? We want to apply f, but we cannot really do this because f, remember, f is just a map from M to R, right? There's no notion of derivative with respect to lambda on this codomain M. So actually this f is f after gamma, and this f over here, right, once again, we cannot differentiate with respect to x mu because the codomain is M. So actually this f over here is f after phi inverse. Now let's break down what each of these terms mean. On the left hand side over here, we first have f gamma is a map from 0 to 1 to r. And so this parameter lambda, right, it makes sense to take this derivative. It's just single variate calculus. Then on the other hand, we have this term over here. What does that term mean? That term means that we have f after phi inverse, right? What is that a map from? It's a map from rd to r. And because the x now is the codomain, right, we can take partial derivatives with respect to that. What this is actually saying geometrically is we're actually saying that we have a manifold M and a point P. We are varying each parameter individually, independently. So for example, if let's say this P, if we increase the value of x1, right, then perhaps it'll define a curve that brings P along this direction. If we increase the value of x2, then perhaps it'll bring us this in this direction. If we increase the value of x3, perhaps it'll bring us along this direction. And we are finding, right, how the function, how the temperature changes along each one of these curves. So for example, if we take a step in the x1 direction, perhaps it brings us to a hotter location. It brings us a step in the x2 direction, it brings us to a colder location. And each time we change one of these parameters, right, we are actually keeping the rest constant. So we're actually keeping, in this case, we're actually keeping x2 and x3 constant and not changing them. And that's what the partial derivative exactly means. We're changing one parameter in the codomain while keeping the rest constant. In a concrete example, right, let's say we have r2, and then we are using polar coordinates. If this is our point P, then our radial direction will be this. We're increasing r, and polar coordinates, increasing theta will bring the point P along this line. And we're asking how the function f, right, how the temperature changes as I move in these independent directions. So that's what this partial derivative is over here. Now lastly, what is this dx mu over d lambda, right? This dx mu over d lambda is actually phi after gamma. What is phi after gamma? Phi after gamma is a map from 0 to 1 to r of d. Gamma defines a curve along the manifold, and phi would tell us what the coordinates of each point on this curve is. In essence, right, this dx mu over d lambda term is telling us how each coordinate changes as we move along the curve lambda. So this point on the curve has coordinates x1 all the way to xd. This point gives us a different coordinate, a different value for the coordinates, and this point gives us different value of the coordinates as well. And we're asking now how each one of them, right, changes when we move along the curve lambda. In essence, right, what this entire statement is saying is that we're breaking down a map f composite with gamma into an intermediate coordinate dependent representation. And now, right, we consider this part, and now when we take the derivative of this with respect to lambda, this becomes a chain rule, where this was a function from 0, 1 to r, this was a function from 0, 1 to rd, and this is a function from rd to r. We take the derivative, we need to do the chain rule, and that's how we arrive at this expression. Now abstracting f away, if we take this expression, we can think of it as d over d lambda equals to sum over all the components. If we can think of this as breaking down a vector, right, into its components and basis vectors. And that is how we arrive at the definition that the partial derivatives are the basis vectors. Now, going back to the issue of many to one mapping, right? How do we define an equivalence class such that the mapping from many to one becomes one to one? The answer now is that given two curves gamma 1 and gamma 2, with their corresponding parameters being lambda 1 and lambda 2, right? We define two curves to be equivalent. So gamma 1 equivalent to gamma 2 if this condition, if the derivatives are equal for any function f on the manifold. Now whenever we have an equivalence relation, we must check, there's three conditions that we must check for. We must check there's reflexivity, I think that's quite obvious. We must check that it's symmetric, which is also pretty obvious. And we must check that it's transitive, which is also pretty obvious. What is not obvious, however, is that this is independent of any function f. What this means is that perhaps it's equal for some function f, but what if we chose a different function g, are the two equal? We haven't proven that if we work for function f, right, then it works for any function g. And so now we'll try to prove that it is actually well defined as an equivalence relation, that it is independent of any function f. So the reason why I went through all the machinery previously is because it is now very obvious when we expand it in terms of bases. This can be expanded in terms of bases, and on the right hand side it can also be expressed in terms of bases. Now we see that if these two are equal, because the right term is the same, if this is equal, that must imply that all these components are equivalent as well. And if all these components are equal, right, then if we replace f with g, then these two sides will be equal as well. In other words, by expanding these vectors in terms of their bases, right, it becomes very obvious that two vectors being equal or two curves being equivalent would imply that their components are equal. And if their components are equal, then that will mean that any function g that we plug in, right, when expanded in terms of the components, basis vectors, they are equal as well. So this is in fact a well-defined equivalence relation with these three conditions being trivially checked. And so now for any curve gamma, right, we actually consider the equivalence class, and now this equivalence class has a one-to-one mapping with the tangent vectors at a point P. So now we've addressed this many-to-one issue, right, by defining equivalence classes of curves, and all that actually remains to do is to show that the vector space that we have defined is closed under addition and can be scaled. The scaling is actually really easy if it just corresponds to the speed at which the curve progresses at. So for example, if this curve gamma 1, right, defines at some tangent vector v1, right, and then let's say we scale this v1 up to v2, right, so v2 equals 2v1, then the corresponding curve gamma 2 is just twice as fast. So if these are equal intervals along gamma 1, right, then this is the interval. Let's say this is lambda, let's say this is lambda plus 0.1, lambda plus 0.2, and this is lambda plus 0.1, right? It's just twice as fast. The same curve, but twice as fast. However, this addition part, right, is slightly trickier because what we must show is that we must show that there is some curve gamma that would represent your vector v when you add two vectors together. And this requires quite a bit of observation, and I'll link a video in the description because the derivation is almost an hour long. The YouTuber XYLYXYLYX has gone through a very detailed video of that derivation, and I want to keep the video short. So in summary, right, we motivated why we need tangent vectors is because we want to define velocities for a point particle on a manifold. We saw that curves on a manifold gives us a very natural way to bring us from a point P to a point P prime, right? So we like to use curves to define our tangent vectors, but there was an issue where there's a many-to-one problem. Many curves could represent the same tangent vector, and we solved that using equivalence classes by saying two curves are equivalent if they satisfy some condition, and the condition is that it maps to the same tangent vectors. We solve it with this clever definition, and now our equivalence classes of curves maps to tangent vectors one-to-one. Now checking the scaling and the addition arguments, right? Addition is done in this other person's video. Scaling is a simple picture. And what we then went on to do was we then went on to define the basis vectors. The basis vectors are partial derivatives in some coordinate chart. The components are these derivatives, and any general vector can be decomposed into the basis vectors, into a linear combination of these basis vectors. And we made sure that this decomposition, right, which is actually a chain rule in multivariate calculus, we make sure that this decomposition actually makes sense from a mathematical point of view. And that pretty much wraps it up for tangent vectors of a manifold. And there's many more things to go through. For example, if we have a compatibility condition for the differentiable structure within two coordinate charts, right, how does that translate to the basis vectors? That will give us actually transformation of tensors, and that will shine light on the definition that a tensor is an object that transforms like a tensor, the circular definition that often confuses physics undergraduates. But that's for another video. I hope that this video of tangent spaces helps motivate the definition a bit more. If you enjoyed it, please leave a like and subscribe, and I'll see you next time.